NASA recently hosted a major event showcasing dozens of stunning images from multiple missions tracking the interstellar Comet 3I Atlas. They highlighted its amazing tails, jets, and multi-planet observation. But one crucial detail was never mentioned: the size of the object itself. Why would NASA omit such a fundamental fact? What does this silence imply? This omission opens a door to questions no official answer has yet closed. When discussing any comet, size is the critical baseline metric. It is the anchor on which all interpretations rest. Without knowing how big 3I Atlas really is, scientists cannot accurately estimate key factors like how much mass it's losing, how much sunlight its dusty coma reflects, or how powerful its jets of gas might be. These physical properties directly scale with the size of the nucleus. Think of it as trying to know the strength of a fire solely by its smoke without seeing the flames. Estimates of 3I Atlas's nucleus size come from several observations, but remain uncertain due to the brightness blending with its thick coma of dust. Hubble images from August 2025 suggest the nucleus could range anywhere from about 1,400 feet, 440 meters, up to 3.5 miles, 5.6 kilometers, in diameter. This is a large uncertainty, yet even at the lower end, it's similar in size to other significant cometary bodies we've studied. This range matters because it frames everything else about the comet's activity and origin. To put this in context, compare 3I Atlas with the first two known interstellar visitors, Oumuamua and Borisov. Oumuamua was an elongated object only a few hundred meters across, while 2I/Borisov had a nucleus roughly a kilometer wide. 3I Atlas dwarfs both, with its coma, the visible cloud of gas and dust, expanding to tens of thousands of kilometers, larger than Earth in diameter at times. Such observations point to a startling conclusion. 3I Atlas is not just another small rock passing through. It's a massive, highly active comet, unlike anything seen before from interstellar space, possibly shedding mass 1,000,000 times greater than Oumuamua. This escalation forces us to reconsider the population and nature of objects wandering in our galaxy, raising significant questions about how such a large, active comet escaped its parent system and how it has survived the long journey through the void. All of this, however, has been understated and omitted in the public releases from NASA, leaving the true scale and significance of 3I Atlas in the shadow. The significance of 3I Atlas becomes even clearer when compared to previous interstellar visitors. The first, Oumuamua, was a peculiar cigar-shaped object roughly a few hundred meters long. The second, Comet Borisov, was around 1 kilometer across. Both were remarkable, but relatively modest by cometary standards. In contrast, 3I Atlas presents an entirely different scale. Observations from multiple telescopes, including Hubble and ground-based observatories, reveal a coma that extended tens of thousands of kilometers, at times wider than Earth itself. This is not just a dusty envelope, but a massive, highly active cloud of gas and dust enveloping the nucleus. The data suggests that this comet is shedding material at a rate far beyond previous interstellar visitors, implying a nucleus that is orders of magnitude more massive. Estimates place 3I Atlas's total mass as possibly up to 1,000,000 times greater than Oumuamua's, though precise measurements are challenging due to the dense coma obscuring direct views of the nucleus. This massive size and unusual activity require a re-evaluation of our expectations for interstellar objects. If 3I Atlas represents a sizable fraction of the interstellar comet population, it raises profound questions about how such large bodies are ejected from other star systems, how common they might be, and what surprising physics might govern their formation and journey. Yet NASA's public statements have largely focused on visual spectacle and the collaborative nature of the observations, carefully avoiding explicit emphasis on the sheer scale and statistical improbability of this object. That omission leaves scientists and observers alike wondering, how does 3I Atlas fit into our understanding of interstellar space, and what else might be lurking unseen? This question marks a turning point, one that invites deeper inquiry into an anomaly that promises to reshape our conception of interstellar visitors. The detection of 3I Atlas challenges basic expectations about interstellar objects. If these visitors come from distant stars randomly with a broad range of sizes, smaller objects should be far more common and thus more frequently detected. This is a fundamental principle in astronomy and planetary science. Smaller bodies outnumber larger ones by many orders of magnitude. The first interstellar object, Oumuamua, was a small, cigar-shaped body only a few hundred meters long. The second, Comet Borisov, was about a kilometer across. Basic probability suggests that among the first three detected interstellar objects, the largest should not suddenly jump to something possibly thousands or even millions of times more massive. Yet 3I Atlas appears to be that statistical outlier. Imagine rolling a standard 6-sided die 3 times. Rolling a low number, then a medium number, is quite normal. But if the third roll comes up a 6, an extreme, it would raise questions about the fairness of the die or the assumptions about it. Similarly, the size and activity of 3I Atlas feel like that improbable outcome, prompting astronomers to wonder whether our models of how many and what size interstellar wanderers exist are missing key factors. This statistical anomaly is not just a curiosity. It represents a real tension between theory and observation, a red flag signaling that something about interstellar objects, their origins, or our detection methods is not fully understood. Yet official communications from NASA and the broader astronomical community have been cautious, providing detailed imagery and observed facts while carefully sidestepping direct discussion of how unlikely 3I Atlas's size and activity are. This leaves a space for ongoing scientific debate and a push for new models that can accommodate this anomaly. Ultimately, 3I Atlas invites us to rethink the story we tell about objects drifting between stars, not just as isolated visitors, but as complex, diverse populations whose detection challenges fundamental principles in astrophysics. NASA's handling of the 3I Atlas event is curious in its restraint. Despite releasing many striking images and detailed observations from a broad array of spacecraft, including Mars orbiters, solar observatories, and asteroid explorers, they have steered clear of addressing what many experts see as the most critical clue: the comet's enormous size and the implications thereof. During a major media event, NASA highlighted multi-mission efforts and foregrounded the comet's beautiful and complex tails, jets, and activity. Yet they omitted any clear commentary on the massive scale of the comet's nucleus or the statistical improbability of encountering such a large interstellar visitor so soon. Instead, the narrative focused on the safety of Earth and the technological feat of global observation coordination. This silence may reflect scientific caution, acknowledging uncertainties and avoiding speculation in public forums, but it also reveals a tension often present in large organizations: the challenge of balancing exciting discoveries with the rigorous standards of confirmed knowledge. By sidestepping the anomalous nature of 3I Atlas's size and the questions it raises, NASA leaves an important gap in public understanding. This gap invites questions about whether institutional bureaucracy, risk management, or a natural hesitation to highlight anomalies hinders the open scientific discourse this object deserves. It is not a conspiracy. Rather, it is an example of how scientific communication sometimes prioritizes clarity and consensus over confronting complex, unresolved mystery. For the scientific community and public alike, this quiet is as telling as any press release. It underscores the need for transparency and further investigation into an interstellar visitor that refuses to fit neatly into existing models. Beyond its massive size and unusual activity, 3I Atlas continues to baffle with its trajectory. Unlike what would be expected from a random interstellar visitor, its path is strikingly aligned with the plane where most of the solar system's planets orbit, the ecliptic. This near-perfect alignment is statistically extraordinary, with astronomers estimating the odds of such an event at roughly 1 in 500. This alignment wasn't just a chance cosmic coincidence for lucky observers, it had significant practical consequences. Because 3I Atlas moves so close to the orbital planes of Venus, Mars, and Jupiter, spacecraft and telescopes scattered throughout the solar system could observe the comet from multiple perspectives, turning what could have been a fleeting glimpse into an unprecedented, multi-angle study. This coordination provided a unique, rich dataset by combining views from ground observatories and orbiters around different planets. The comet's retrograde and slightly tilted path, around 5 degrees from the ecliptic, allowed it to avoid Earth directly, posing no threat, yet pass sufficiently close to key observation platforms. The improbability of this configuration underlines how much scientific leverage this object has afforded researchers, while also deepening the mystery. Is it all just a cosmic roll of the dice, or could this alignment hint at unknown physical or dynamical processes shaping how interstellar objects enter planetary systems? Some have speculated on possible observational biases, or even suggested that unknown forces guide such objects preferentially along the ecliptic. NASA's official narrative celebrates the success of this multi-planet observation campaign, but remains silent on the deep statistical implications, leaving viewers with a nagging sense that 3I Atlas's story is part coincidence, part puzzle, and all worth a closer look. 3I Atlas forces us to question fundamental assumptions about interstellar objects and how they reach our solar system. Its massive size, unusual activity, and improbable alignment with the ecliptic plane collectively challenge the prevailing models astronomers use to understand the population and behavior of interstellar debris. Our models predict that most interstellar debris should be small, inactive, and randomly distributed in direction, a background hum of cosmic rubble. Yet, here we have a massive, highly active comet appearing unusually aligned with the solar system's plane. This could mean several things. Perhaps the process that ejects objects from other star systems favors larger bodies or specific trajectories, a nuance overlooked in current theories. Alternatively, observational biases may be at play. Our detection tools are most sensitive in regions populated by solar system planets, inherently skewing the findings toward objects aligned with the ecliptic. It's possible that we only observe a fraction of the interstellar population, missing many objects with different trajectories or sizes. There is also the possibility that 3I Atlas formed under rare or violent conditions, producing unusually large and active bodies that defy the typical picture of interstellar visitors. If so, it broadens our understanding of the galaxy as a dynamic environment where diversity and anomaly are the rules, not exceptions. NASA's cautious public communications reflect this uncertainty. They highlight remarkable data while avoiding firm claims challenging our theoretical framework. This ambivalence invites us to remain open-minded, embracing anomalies like 3I Atlas as opportunities, not threats, to scientific progress. In summary, 3I Atlas is a puzzle and a prompt. Our cosmic neighborhood is more complex than we imagine, and our understanding must evolve with each surprising visitor. Beyond its size and trajectory, 3I Atlas continues to perplex scientists with its unusual chemical composition. Spectroscopic observations from the Very Large Telescope revealed significant emission lines from neutral nickel vapor in the comet's coma, an unexpected find, especially because iron, a metal commonly paired with nickel, is virtually absent. This nickel-to-iron imbalance is highly unusual, diverging sharply from known solar system comets, where nickel and iron usually appear together in similar amounts. The comet's nickel emission was first detected in July 2025 and steadily increased as it approached the Sun. By August, 3I Atlas was estimated to emit around 4.6 grams of nickel per second, alongside cyanide gas. This discovery deepens the mystery, because standard comet chemistry involves metals and compounds released together as ices and dust sublimate. Yet 3I Atlas violates this pattern. Researchers have proposed various explanations. One intriguing possibility is the presence of nickel-bearing organic compounds, such as nickel tetracarbonyl, which can decompose under space weathering to release nickel vapor selectively. This molecule is volatile, easily broken down by ultraviolet sunlight, potentially explaining the high amounts of nickel observed even at large distances from the Sun. Additionally, measurements by the James Webb Space Telescope revealed that 3I Atlas's dust is overwhelmingly carbon dioxide rich, about 95%, with very little water or carbon monoxide, a composition unlike any comet previously studied. The decoupling of nickel from iron and the unusual carbon dioxide dominance suggests that 3I Atlas formed in an environment quite different from typical cometary nurseries in our solar system. While this does not point to any artificial origin, it highlights the comet's unique chemical story, challenging existing assumptions about interstellar comet composition. In short, 3I Atlas's chemistry adds fresh chapters to the cosmic puzzle, demonstrating that even familiar materials may behave unexpectedly in alien contexts and offering new clues to the diversity of planetary formation across our galaxy. As 3I Atlas passes through and beyond our solar system, the scientific focus shifts to what lies ahead. The comet reached its closest point to the Sun, or perihelion, on October 29, 2025, at about 1.36 astronomical units, roughly the distance between Earth and Mars. At this closest approach, it raced by the Sun at speeds up to 68 kilometers per second. After perihelion, 3I Atlas continued its outbound path, moving away from the Sun and Earth. Although it won't come closer to Earth than about 1.8 astronomical units on December 19, 2025, this distance still allows for continued monitoring using powerful telescopes and planetary spacecraft. Observatories on Earth and space-based platforms like the James Webb Space Telescope are poised to track changes in the comet's coma and tail as solar heating wanes. In addition, spacecraft orbiting Mars and other planets are expected to intersect or come close to the comet's extensive ion tail in the coming months. This provides a rare opportunity to directly study how the solar wind interacts with an interstellar comet's outflow, yielding insights not just into 3I Atlas, but into plasma physics and solar system boundaries. Upcoming observations will focus on refining size estimates, jet behavior, mass loss rates, and detailed chemical composition. These data will help resolve ongoing questions about the comet's origin, structure, and unusual chemical fingerprint. Over the next year, scientists anticipate a steady unfolding of answers, as well as potentially new mysteries. For now, 3I Atlas remains a symbol of cosmic curiosity, a visitor from beyond, inviting us to observe closely and rethink what we know about the universe's small but intriguing travelers. If this journey into the mystery of 3I Atlas has sparked your curiosity, subscribe for more deep explorations into the unknown corners of space. Share your thoughts and questions below. What do you think 3I Atlas is really telling us? Stay tuned as science continues to unfold the secrets of this extraordinary visitor.